Hello everyone, I'm Dr. Engineering. Welcome back to my FPGA tutorial series. Did you know that multiplexers are a fundamental component in almost every digital device, from smartphones to computers? These small circuits help manage and route signals efficiently, allowing millions of operations to happen seamlessly. By the end of this lesson, you'll understand what is multiplexer and how to design it. Multiplexers are everywhere in digital circuits. They are crucial in situations where we need to control data flow, such as selecting between different data buses in a CPU, or switching between multiple data sources in communication systems. By learning how to design a multiplexer, you'll gain an important skill for digital circuit design. In today's lesson, we'll focus on designing a 4-to-1 multiplexer using VHDL. A 4-to-1 multiplexer has 4 inputs labeled I0, I1, I2, and I3, 2 select lines, S1 and S0, and a single output, Y. The select lines determine which input is passed through to the output. For example, if S1 S0 is 0 0, input I0 will be selected and sent to the output. If S1 S0 is 1 1, input I3 will be sent to the output. Essentially, the MUX acts as a data selector, and it can reduce the complexity of your circuit by efficiently managing multiple signals. This is the truth table for the 4-to-1 MUX. As you can see, depending on the combination of select lines S1 and S0, one of the inputs, I0 to I3, will be sent to the output Y. This truth table helps us understand the behavior of the MUX and how the select lines control which input is chosen. Next, let's go to Vivado and translate this logic into VHDL code. Just like before, we're going to start by creating a new project called MUX 4-to-1. The steps are exactly the same as when we've designed other projects in the past. Now, let's move to the source panel and create a new VHDL design file. We'll name it accordingly. Based on the block diagram of the multiplexer that we just discussed, we'll define the input and output port names. To make our simulation and observation easier later on, we'll define the 4 input signals and 1 output signal as 2-bit buses. This way, we can observe a range of values for each input. Additionally, we have 2 selection signals that will also be inputs. Here, we'll group these 2 selection signals as a single 2-bit input signal S. So, let's adjust the entity's port declaration according to this setup. Next, based on the block diagram of the multiplexer, we'll write a process to handle the input selection logic. First, let's talk about the process block. In VHDL, a process is used to group a series of sequential statements. The code inside a process block will execute whenever there is a change in any of the signals that the process is sensitive to. The parentheses after process contain what we call the sensitivity list. This list includes the signals that trigger the process to run. So, anytime one of these signals, I0, I1, I2, I3, or S, changes value, the process is executed again. If you don't include the correct signals in the sensitivity list, the process might not trigger when you expect it to, which can lead to incorrect behavior. That's why the parentheses are important. They tell VHDL when to re-evaluate the code inside the process block. Next, we have the case statement. The case statement is similar to a conditional statement, like an if-else, but it's specifically used when we need to select one option from several possibilities. In this case, we are using the signal S as the condition. The value of S will determine which block of code gets executed. It's a very clean way to handle multiple conditions without writing a long chain of if-else statements, which can be more difficult to read. For a multiplexer, this is perfect because we are selecting one input based on the value of the select lines, S. Inside the case statement, we have the when clauses. The when keyword specifies what should happen for each possible value of the signal S. For example, if S is 0 0, the output Y will take the value of I0. If S is 0 1, then Y will take the value of I1, and so on. So, each when clause corresponds to a different combination of the select lines S. The final when others clause acts as a safety measure. If S takes on any unexpected value, we set Y to a default value, which in this case is 0. This ensures that the circuit is protected from unexpected states, making it more robust. With that, the design of the MUX circuit is complete. Now, just like before, we'll return to the source panel and create a testbench file. In this testbench, we'll establish the necessary test signals. For the input signals, we'll use the prefixer to indicate that these signals are like registers in verilog. Similarly, we'll use the prefix W for the output signal, which is similar to a wire in verilog, connecting to the output signal Y. Inside the begin block, we first declare an instance of the 4-to-1 multiplexer, which we'll call UUT. We'll then map the signals accordingly using the port map. Next, we'll design another process to control the input signals and simulate how they change over time. To make it easy to track changes, we'll assign specific values to the 4 input signals. Let's set the 4 input signals to decimal values 3, 2, 1, and 0 respectively. This ensures that each input signal is distinct, which will help us observe the output behavior clearly. Then, we'll design the selection signal S to cycle through all possible values, from 0 to 3. This way, we can cover every possible combination. We'll also make sure that the interval between signal changes is 10 nanoseconds to give us a clear simulation of each scenario. With that, our testbench is fully designed. After making sure everything looks correct, we'll go ahead and click on Simulation Settings to adjust the simulation time to 50 nanoseconds. Now, let's run the simulation. Once the simulation is running, we'll click Zoom Fit to get a better view of the waveform. To make things easier to read, we'll also change the value display to unsigned decimal. As we can see in the waveform, the 4 input signals hold their respective values without changing. However, as the S selection signal changes, the output signal Y connects to the corresponding input signal. For example, when S is 0, Y is connected to I0. When S is 1, Y is connected to I1, and so on. This matches exactly what we expect from our design, meaning the multiplexer is working perfectly. And with that, our MUX design is complete. Practice makes perfect, so keep experimenting and soon you'll become FPGA experts. If you like this tutorial, please subscribe my channel for more useful information. See you in the next video.